Hello and welcome to the Engineering Dynamics Course Companion. We're in class 22. We're in Kinetics of Rigid Bodies, and today we're going to talk about energy methods. As always, you could just jump to the examples by going down in one of the links below, somewhere down there in the table of contents under the description. So for our bottom line up front, we had in particles, which is way back in, I don't know, maybe it was class 10 and 11, maybe? Yeah, right around there. In class 10 or 11, we had work and energy, and we dealt with, the kinetics. We dealt with potential energy, kinetic energy. Well, just like that, and work energy for rigid bodies, we have all the same things, but now we have a rotational contribution right there. And how that shows up when it's for kinetic energy is we have 1/2 mass moment inertia times angular velocity squared. When it comes for work that's being applied, we can now, in addition to the force times the distance, we can have mass times angular displacement right here, and we know that we want to integrate it. Now, you don't want to double dip on things, so we will be careful on that, because we could sometimes look at a force times a distance that's happening, and we could find that we could also describe it with the a moment times an angular displacement. We don't want to do both of those in terms of the situation, so be on the lookout for that. Okay, so here are work and energy applied. Okay, so I guess I put all these things onto one page. Here is that equation, the big equation for work and energy, right? We have the energy before plus what something might happen to it times equals the final energy, right? So we have before, something happens to it, final energy. And now the kinetic energy is the total amount of kinetic energy that's taking place. So that could be the mass times the velocity, let's say, of the basket of apples, but also the kinetic energy of the drum, because the drum in this case is large enough that it's going to affect the outcome, right? So this rotational moment kinetic energy. We can also have work, as we found before, was force dotted against the position vector. So what we end up having is force through a distance that gets traveled, and if the force is constant, it could be force times delta x that's taking place. But now we can also have, if something rotates, we could have the moment times the angular displacement. But how are these two things can actually be equivalent to each other? Because as if you take a look and we were to move this force as it moved along right there, we would have the path, that delta S, if you will, that's being placed right there, would be equal to that radius A with respect to B times delta theta. Right there, right? That would be the arc length, right? So that force that's being that's going on right there is following along, right? Well, also, so the energy would be that force FB, right? So if we had the energy of that thing that's taking place between there, maybe F times RA with respect to B times the delta theta. But wouldn't the moment that would be placed on here, or the equivalent moment, be that force times this right here? So that right there is actually the moment, or the MA as I've drawn here, the moment that's happening about A. So you wouldn't use both of these onto there because they're really equivalent to each other, right? So you want to be careful not to double dip just because you could write the moment in a different way. That moment is really being caused by that force, so it's not both of them in there. And then we could also, it's possible to have another form of potential energy here with respect to rotation, that we'd actually have a spring that's a rotary spring. And you can see here that I've cleverly put this as cheese inside there. It's a mousetrap type. You could think of a rotate, one of the versions of a spring might be a rotational spring, in a mousetrap, or in a wind-up toy or in a clock. Those are torsional springs, but they hold potential energy as well. All right, so here's the example that I put together. And so we have this block A, and it's on a slope right there where it's 60 degrees right here. So it's 60 degrees right there. And the block C is connected to block A by a rope that doesn't stretch. And it's going through a large frictionless pulley. So the pulley is large enough. This pulley B is large enough that its mass is gonna matter. So it has a mass of 60 kilograms and a radius of 0.25, and I believe we could treat that like a disc. The other two frictionless pulleys have negligible mass right here. So these guys, they're small and their mass doesn't matter. Both of the blocks are released from rest and they begin to move. The spring that you see has a spring constant of 2,000 newtons per meter, and it's connected to block A. At the beginning, it's going to be stretched 30 millimeters, right? So it starts out already with some stretch to it. The coefficient of friction between block A and the slope surface is 0.25. And so we want to find the velocity of B after it's moved 0.5 meters. Now, truth is, it could be going upwards, right? That spring could have been strong enough so when you release the thing, it actually pulls the thing down. But we should probably have checked that. Do I say that I checked that? We'll see. So I got the mass moment of inertia of the pulley because I want to include some of that in the kinetic energy of it. So we want to label some datums. That's always a good idea to have what we consider the bottom of the thing, or all the references, so we have change of heights. But we also want to have some datums so we can do the dependent motion of the pulleys, because this is also a pulley problem. So in my pulleys, I see from there that I'm going to have this length of 3, right? So that SA, there's 3 of them right there, yes, and then 1 right here. So we see there's a 3-to-1 ratio of the velocities. That's really what we're going to need with work or energy. And let's see, if we assume a time increment right here, right? When you have that velocity type of relationship, you could also assume a time increment and multiply by it, and now you have like a distance relationship, right? So that x prime, that we're saying that this is the x prime direction right here. I labeled it down over here. That x prime direction that the thing is moving right there is going to be related by 1/3 of the delta y right here. So here's my delta x prime. I drew it in there, right? So we want to have some type of amount of relationship between the motions, not just the velocities. The reason why I do that is because I can't use this as the relationship because that has the length in there. But if I get it to the velocity and then I multiply it by a delta t, now I'm able to get what the delta position is going to be, so I can have that relationship, tying the two things into each other. We want to find the vertical change of the block after it's moved 0.5 meters, right? So we know it went down 0.5 meters. So we were able to find okay, so we found what the distance that it moved along the slope was 0.1667, and now we're able to find the amount of vertical change of block A is 0.1443. 0.1443. And now the angular speed of the pulley, we can relate that to the velocity of C by way of just a simple what the tangential velocity is along the edge of pulley B is going to be equal to the velocity at C. Therefore, we can write out what that angular velocity relationship is going to be. So here's the FBD and the IBD pair. They showed up there. I didn't make them. I guess I didn't make the animation so that the thing showed up when I wanted it to. And truthfully, the IBD is not really necessary in this case because we're only looking for what's going on in the y prime direction. Our purpose there is to try to get what the normal force is, so we get what the friction force is. But this is good practice to keep drawing both of them in there. So in the y prime direction, we set that equal to 0, and we're able to get the relationship between the normal force at A and we put in what the weight is. That's the mass 20 times the 9.81 acceleration of gravity, and we're able to get the value of the normal force. And with that, we're able to get the value of the friction force. And we weren't even given the static coefficient of friction, but there is some wild case where all the masses and that kind of thing were, or the spring constant and everything could be set so that the thing wouldn't move when you released it. But we're going to go ahead and assume that it does move and that C is going to be moving downwards. But something we might want to check just to double check for ourselves. So as always, what's really good idea when we're doing this problem, and I should have done it, is to write out the full kinetic energy equation right here, right? And then so we can think our way through the thing and then start populating it, right? So here is kinetic energy 2 plus potential energy 2, right? So, and we're only going between two states. We showed in an earlier example that we could go through multiple states, but we only need to go through two states in here. So the potential energy at the beginning right here, we've got to remember that the spring has been stretched. We also want to make sure that we're careful that the spring is going to have an additional amount of stretch after block C moves down and block A moves up, so that's going to stretch it even more. So we want to be careful when we go to put in what the displacement is in the second position. And then we have right here, we have the potential energy of block C only. Now, going back just a little bit, we made our datum for C down here so that in state 2, it's going to be 0. Now, and then we made our datum for A right here, so its potential energy at state 1 is 0, right? Because it's going to increase in potential energy, whereas block C is going to decrease. So that was one of our strategies in putting through there. Okay, so now the work that's energy that's being taken away from there is going to be the friction force times the displacement up the slope, but it's going to be negative. And it's negative because energy is lost, or the other thought process is that the force of friction is going downwards, whereas the motion of the block is going upwards. They're opposite from each other. And, this force dotted against motion, that dot means cosine of 180 degrees, it's negative, right? Or just thinking that they're opposite from each other, therefore they're negative. The kinetic energy at state 2, now everything is moving. We have block A, we have the pulley as a rotation, and we have block C, right? So all of those are taking effect, and we're also able to stick in that relationship here and that relationship here. So there is this right here is from dependent motion, and this right here is from the relationship of the pulley, right? The tangential velocity of the pulley on the edge of the pulley was equal to velocity c, and it was convenient to use velocity c because that's the thing we want to get at the end anyway. So potential energy in the second state, we want to be careful here. Okay, so it has moved up the slope this amount. So that's an additional amount of stretch, right? It's being stretched this amount. It gets stretched even more. So now it has even more of deflection, therefore more potential energy. And then, as we mentioned previously, the potential energy of block A is going up as it goes up the slope. And we could write all these things out, right? So I like to write the equation up before I do these things as my means of here is my organizing thoughts, right? As I'm trying to get up here, but I wrote it down here instead. And I plug all of those things in there. And it's nice to kind of see the contribution, by the way, of each of these pieces, right? Okay, so here's the initial potential energy that was taking place. Here's what got robbed out of here. And here's what the final potential energy is going to be, right? So there's still, there was a trade-off between potential energy. Some of the potential energy was due to the block C coming down, but then some more was created into the thing. And then some got stolen away, and then what was left turns into kinetic energy, and we're able to find, we take the square root right there. and we're able to find what that velocity is. Mindful, if you end up with a negative number and then you have to take the square root of it, you've made a mistake somewhere. So that's another good thing to do with where you have these in-between steps where you're finding out the magnitudes. They really do try to help you try to isolate. It's like, okay, what could have gone wrong if we get something that doesn't make physical sense? Right, so that is the answer. Velocity at c at state 2 is 1.87 meters per second. So that wasn't too bad, but you could do a lot of different things with the work energy. It tends to be a really useful and more straightforward. Quite often, it'll be an approach that you'll want to use for even more advanced things. Like there are other types of dynamics that you could approach things with, and that quite often they will deal with energy methods because it is a very useful method. All right, so for more examples, please check out the Engineering Dynamics course companion. Parts 1 and 2 are available in soft cover here. They're also available in hardcover. They look pretty nice. I like them. It's a good coffee table book, right? And it's full of cartoons and full of examples, more examples than just here. I do about I do one example out of each of these chapters. Every chapter has at least 4 examples of varying degrees of complexity. Have really nice diagrams. And once again, the cartoons are meant to not only be sort of a little fun, a little entertaining, but also leave you with something that you could remember. So go down to the links below in the description to go to the publisher. You could also go to Amazon and consider subscribing to the channel. And me and Wormy would appreciate that. Leave some feedback. Say that you were here. Just, thank you.